Gnanam paramam dheyam. Knowledge is supreme.
Earlier we have discussed vibrations of diatomic molecules, okay, and we have discussed that you can model diatomic molecules as a first approximation as harmonic oscillators, and then since diatomic molecules must break eventually if the vibration is too much. So, that is why what you have is you have to use anharmonic oscillator model if you want a little more accurate picture, right. So, now when you talk about polyatomic molecules, how do I handle the problem? You might remember from your elementary physics course, or maybe you have studied it in thermodynamics course in chemistry as well, that when I have a molecule with say n atoms, some molecule like this, n number of atoms, the way you formulate the problem of motion of these atoms is you consider 3 axes to be associated with each of these atoms, right. So, what is the total number of coordinates? 3n number of independent coordinates, right. Whenever I say coordinates, what is implicit is that they are all independent of each other. What is another word for independent in this context? Yeah, x, y, z are independent of each other. If I want to replace the word independent by another word, what would I say? Yes, orthogonal to each other, very good. What is another word I can use? Yes, decoupled is okay, but another a synonym of orthogonal in this context. Are they normal to each other, right? So, this normal modes of vibration, when I talk about that, I do not mean that there are crazy modes of vibration, no abnormal mode of vibration. What I mean is I am talking about vibrational coordinates, independent modes of vibration, okay. We will come back to that. So, total you have 3n number of coordinates, and then how many of these should be reserved for translation, how many for rotation? 3 Rx, Ry, Rz we discussed yesterday, remember. So, number of, I can do it here, number of normal modes of vibration is equal to 3n minus 6 for a linear molecule and 3n minus 5 The good thing about a chalkboard is that if you forget something, you can always write it later. So, 3n minus 6 for a nonlinear molecule, 3n minus 5 for a linear molecule. Alright. Now, so I think you know this, right, that a molecule has 3n minus 6 vibrational degrees of freedom. So, normal mode is just another word for a vibrational degree of freedom, but it is important because we should not forget that we are talking about vibrations that are independent of each other. And since we have taken these 6 out, we are talking about pure vibration. What is the meaning of pure vibration? No change in, well, pure vibration means there is no rotation, no translation. What is the meaning of translation? Change in, if you put in very simple terms, change in the position of center of mass of the molecule. If the center of mass moves, then it is translation. So, when we talk about vibration, what we say is that the center of mass remains in place. If the center of mass moves, then it is no longer pure vibration, it is vibration plus translation. So, in these normal modes of vibration, center of mass does not move. It is very important to remember that. You have taken out 6 coordinates already. Now, so if that is the case, you can understand that when we talk about vibration, let us come to this hypothetical molecule. What is the meaning of vibration? Relative motion of the nucleus, of the nuclei. So, let us say this, let us only consider this bond. If you want to say that I have vibration only along this bond and nowhere else, then what will happen? This atom will say move here, okay, but would that be a pure vibration? If only this atom moves and nothing else, that would not be a pure vibration, isn't it? Because if only this atom moves, that means the center of mass has moved. Is that right or not? Center of mass would have moved. So, to compensate for that, other atoms also have to move in some way, so that center of mass position is not changed. Okay? It is perhaps a little easier to understand if you draw a more tangible molecule. Water. Let us consider that I have a vibration in which this OH bond is getting stretched. So, you can understand that if this OH bond becomes stretched like this, center of mass would move. How can I compensate for this movement of center of mass? I can pull the other hydrogen atom out as well. So, I can compensate for the stretch of this bond by stretching the other bond. Let us see. So, how can I compensate for that? And since oxygen is so much heavier than the hydrogen atoms, oxygen has to move only a little bit. Okay? So, if I draw the arrows like this is a valid pure vibrational coordinate. Okay? I could also do something else. This one stretches, I can say that I will move this hydrogen, I will make the other OH bond shorter. Okay? Now, in which direction does oxygen have to move? Now, what I am saying is that I am trying to compensate for the vertical movement by moving hydrogen towards oxygen. So, so the horizontal movement has to be taken care of. In which direction does oxygen have to move, this or that? Yes. This is another kind of vibration it can have, or I can do something else. I can have this kind of motion. I think you guys already know this. I am just repeating, but I am repeating because this will help us go somewhere. This, what kind of vibration is this? Bending. You can say scissoring, bending is more common. So, here you see what is the difference between the first and the second. In the first kind of vibration, the two OH bonds stretch at the same time and get compressed at the same time. Okay? So, this is called symmetric stretch. We will usually denote normal modes by the letter xi. So, this is the first normal mode, symmetric stretch. It is not very difficult to guess what this will be. Here, when one bond gets stretched, the other bond gets compressed. So, this kind of motion. What is it called? Asymmetric stretch. Xi2, asymmetric stretch. And this is the bend. So, let us say this is Xi3. So, between stretch and bend, which one do you think has higher energy, which one has lower energy? Stretch has higher energy, bending requires a smaller energy. So, you go to a circus, sometimes you find strong men who can bend an iron bar. Have you ever seen a strong man who can stretch an iron bar? So, that would require the strength to be much higher, right. So, what we will do is we will just show you, unfortunately I have forgotten to include it here. So, we will show you the character table of C2V. And now, let us convince ourselves that these normal modes also form basis for some symmetry species or the other. Before that, what is the meaning of normal modes? Once again, modes that do not have components along each other, okay, which are independent of each other. How do I convince myself that these are actually normal modes? For water, we can do it intuitively. There is no way in which you can write this as a linear sum of this one and that one. Okay? We will do carbon dioxide after this, and then we will see what happens when things get a little more complicated. Okay? But do not forget that these are modes that do not have components along each other. Does this mean that water vibrates only in these three modes? Not necessarily. The actual vibration can be a mixture of these three with different coefficients. Those of you who have taken dance lessons would know that first they teach you what to do with your feet, right. So, the initial lessons are just how to move your feet in a particular rhythm. Okay. Next they teach you what to do with your hands. Finally, in certain dance forms they teach you what to do with your head. And then when you actually do a dance, what you essentially do is you do different linear combinations of the movement of feet, movement of hand, movement of head, right. Those are the normal modes of dance, and you obtain different kinds of dance by just changing the coefficients in the linear combinations that you use. I had said this to a student who danced 2 successive years. I said that you have only changed the coefficient. She was not amused, but then no matter whether you are amused or not, that is what it is, right. So, this is the meaning. So, what we are trying to do is we are trying to work out the normal modes of molecular dance, that is all. Now, let us look at symmetric stretch. Now, if I call this xi1, we need to understand also what is minus xi1. If this is xi1, what is minus xi1? Minus xi1 means all the movement has to be reversed. So, bonds get compressed, this oxygen moves a little down. If this is xi2, you just reverse all the arrows, that is all. So, if this is plus, this is minus, that is all. In the first one, if this is plus, this is minus. In case of bending, if this is plus, this is minus. So, let us look at xi1. Where does it belong? Apply E to xi1. Of course, it remains the same. So, what is the character for E? 1. What is the next symmetry operation? C2. Apply C2. What happens? This hydrogen goes there, this hydrogen goes there. But we are talking about normal mode. So, we need to worry about the arrows. Do the arrows go out or do they come in? They still go out. So, is it xi1 or is it minus xi1? It is still xi1, right? If it was minus xi1, then the arrows would have gone in. Are we clear about this? If you understand C2, we understand everything. So, character for C2 is also 1. What is the next one? Sigma V. All atoms remain in their own place, all arrows remain in their own place. So, character is 1. What is the next one? Sigma V dash. The 2 hydrogen atoms interchange, but arrows still go out, they do not come in. Okay? So, it is plus 1. So, what is the symmetry of this symmetric stretch? A1, right? So, this is, we call this an A1 vibration. What about bend? What about bend? Character for E is 1. What happens when you apply C2? This is bend, this is plus bend, this is minus bend. Okay? When you apply C2, does psi3 become minus psi3 or does it remain psi3? It remains psi3. Are we clear? So, character is 1. Sigma V, what is the character? 1 sure, sigma v dash, this is plus, this is minus, this is plus, this is minus, I am applying this mirror. Is it 1? Is it minus 1? 1 sure 1. So, this is also A1. Let us talk about this. Let us not forget what this is. This asymmetric state psi 2 is this, right. This is plus, this is minus, alright. See, it is normal mode, it is also like a dance, alright. What is the character for E? 1. What is the character for C2? Plus, minus, yes. Apply C2, what happens? This becomes this, isn't it? So, minus 1, sigma V plus 1, sigma V dash minus 1, convinced? So, 1 minus 1, 1 minus 1, which symmetry species is that? I do not even have to look at the character table. Principal antisymmetric with respect to the principal axis. So, it is not A, it is B. Symmetric with respect to that sigma V. So, it is 1. So, it is B1. So, hereby what we have been able to do is, we have been able to perform a symmetry classification of the normal modes of water. Okay. How many atoms are there in water? Okay. Let us think of another kind of triatomic molecule, carbon dioxide. Is carbon dioxide linear or bent? Linear. How does it affect the vibration? Instead of 3n minus 6 vibrations, I should have 3n minus 5 vibrations. So, how many vibrations? 4 vibrations. What will it be? Like water, there will be a symmetric stretch. And in this case, carbon does not have to move. Carbon is at the center, it is a linear molecule. So, the CO bonds stretch, this is plus, this is minus. You can have asymmetric stretch, where this bond becomes smaller, this bond becomes larger without a change in the position of center of mass. That is important to remember. And you can have bend. So, I can draw bend like this in the plane of the board. These oxygen atoms go down, carbon go up, okay. Linear, this is bend. Where is the 4th vibration? So, this is one kind of vibration, one kind of bend. You can have this kind of bend also, 90 degrees. Can I not have this kind of a bend? Why am I not calling it a normal mode of vibration? Because I can easily write it as a linear combination of this and this, okay. Another question, the moment this vibration happens, does not the point group change from d infinity h to C2v? Actually, in the approximation level at which we are working, it does not, because do not forget we are talking about harmonic oscillation. Harmonic oscillation means angular displacement is less than 4 degrees, have harmonic vibration. So, you can still work with the same character table. Okay, where do these belong? Quickly, this one of course is totally symmetric, right. What is totally symmetric for d infinity h? It is sigma g plus. So, this is called a sigma g plus vibration. What about this? What about this? This will be like Z actually. This will be like Z, right, because you can write it as an arrow, isn't it? An arrow along the internuclear axis. Internuclear axis is Z axis. So, it will have the same symmetry as Z. So, that is going to be sigma u plus. Please work it out. If you have a problem, you ask me next day. This is called sigma u plus vibration. What about these? These are two degenerate vibrations, okay. Degenerate vibrations, same energy, and they are along x and y. So, they will have the same symmetry as x and y. What is the symmetry of x and y? Pi u. So, these are pi u vibrations. The reason why we are doing this is that, as we will see later, by using symmetry we will be able to say which of these normal modes are IR active, which are not, which of these normal modes are Raman active, which are not. But before we go there, let me leave you with one question. We could figure out the normal modes quite easily for triatomic molecules, water and CO2. The moment I add one more molecule, suppose I make it BF3, planar molecule, right? What is the point group? D3H, D3H. It does not remain so easy anymore. What is the number of normal modes of vibration? 4 atoms are there, so 3n minus 6, 6, right? Will you be able to guess what these 6 vibrations look like? Not so easy. So, we need some way by which we can work out at least the symmetries of the normal modes of vibration by using character table. So, next day, Thursday, what we will do is we are going to work with BF3 and we will try and see how we can work out the normal modes of vibration without even knowing what they actually look like, right. And then we will talk about IR and Raman activity.